Part C, Mergesort, another sorting algorithm. And this one also very useful. So let's start learning this new algorithm. C.1, Introduction to Mergesort. Why we need to learn a new sorting algorithm? First, let's look at this, our problem, number 13. Here, our problem number 12, I didn't complete it. I still leave. So that topic. Number 12, that's the selection problem. Okay? So just one or two slides left from the previous lecture. So let me put it aside. At some point, I will complete that. Okay? So at some point, I will spend some time to complete number 12. So now, problem number 13. Merge two sorted arrays. A simple, basic computing problem. Let's look at the problem first. Given two ordered arrays. Remember important information here. Ordered arrays. Good property we can take advantage of. How to merge them to get an ordered array. This time, the merge operation. We want to use some very efficient algorithm to merge two ordered arrays to get a larger ordered array. A simple question, but very basic. So we want to study this problem first. Motivation, why we want to study? Okay. So let's look at this motivation question first. Why we need to consider this problem? There is some good reason here. Let me describe the situation we may have here. Let's look at this question first. How to sort a huge array? We know how to sort a general array, right? Let's consider the array could be very large, huge. How large it is? How large it is? 51. Several gigabytes, that large. That large, several gigabytes. The array size. If you store the array data on the hard drive, you need several gigabytes. Is that large? Pretty large, right? Try to imagine. Okay. Yeah. So when in that situation, let me use this line segment to represent that huge array. And one critical condition for this huge array, your main memory cannot hold the big array, the huge array. Your main memory is not large enough to hold the whole array. That condition. Can you still do the sorting? That could happen because usually when we run our sorting algorithm, we load the whole array into the main memory first, right? Usually, right? The whole array. The first thing we need to load the whole array into the main memory. Then we can apply our sorting algorithm. That's the usual way. But imagine this time our data too large. We cannot load the whole array. You can only load subarray into the main memory, but you cannot load the whole That could happen. Yeah. That could happen. So the question, how do you sort that super big array? You have to modify your algorithm. Think about that. Here, let's try to answer this question. Divide and conquer. Because that array too big, we have to divide it into smaller pieces, smaller subarrays. For each subarray, we can load it into the main memory. Okay? For each subarray, we make it small enough to be loaded into the main memory. That's no problem. Yeah. We can assume that. Okay? Yeah. So here you see several smaller subarrays. Then we just look at each subarray once at a time and sort it. Right? Look at sorting. Once at a time. Then after we complete the first round processing, we can sort all subarrays. Right? Here, I assume all these subarrays are in ascending order. Ascending order already. Yeah. You see, each one ascending order. But the whole array is not sorted. Each subarray is sorted. Still, we need the last step to make the whole array sorted. This time, you can see what we need to do is this basic merge step. Right? Merge first two ordered subarrays. Okay? After that, merge another two ordered subarrays. Okay? Until we finish all the possible merges. Under the condition, you cannot load all of your data into the main memory. When you do the merge, you cannot load all the data into the main memory. But you can load part of it, right? Part of it, do processing and put the elements in place. Another part, loading to main memory, put them in place, and so on. At the end, you put all elements in place. That's the idea. Okay? But you need to do that merge step. Basic merge step. So now let's study the merge. How to use the best algorithm to do this merge step. Most efficient algorithm to do this merge step. Right. Also, this way you can think, if we can split in this way, we can do parallel computing, right? Different processors, we send different subarray to different processors, do the sorting, and then we merge those ordered subarrays. Parallel computing to make the whole processing faster. That's another good thing we can do. Parallel computing. Just, let you know we can do a lot of good things. How to that? Now let's work on this basic problem. Given two arrays that are already sorted, how to get a new sorted array that contains all the elements. Here, we want to take advantage of the structure data. order information, very useful. We don't want to throw away that useful information. We want to take advantage of that useful information. The question, how? How do we get some idea related to the ordered information? That's the first connection we're looking for. Connection. We want to connect it with our own experience. Here, what our own experience has some close relationship with this question. Let's look at that. All right. Do not use any sort that does not make use of any order information. At this point, we have learned several sorting algorithms. Some of the algorithms we never use order information, but for some algorithm of them, we use order information. So let's recall first. Right. Selection sort. Do we use order information in the selection sort?
Yes.
If the array is ordered, can we do faster in selection sort if array is ordered? One big probability, the best case, worst case, average case, all the same for selection sort, right? That means we never use ordered information. Best case equals worst case. How do you use the ordered information, right? Yeah. So we didn't use ordered information. Bubble sort. Do we use ordered information in the bubble sort? Best case, worst case, average case, the same also, right? No difference. We didn't use. Yeah. All right. Then another one. Remember, we spent some time to discuss the property. Insertion sort. In the insertion sort, is the order information very useful? Very useful. When the array is already ascending order, can we do it much faster? In the insertion sort, big theta of n, right? When the array is ordered, that's the best case. We only need the big theta of n to complete the insertion sort. But for the average case and the worst case, even average case, worst case, if the order information is not available, we need a big theta of n speed, much slower. That means for the insertion sort, the order information is very useful. Okay? That means here we should make a connection of our current merge problem to the insertion problem. Because at least in the property, making use of the order information, this property, we can borrow some idea from the insertion sort. Okay, yeah, all right. Yeah, because this nice property in the insertion sort, we can use in this special situation when we need to sort an array that is almost ordered, not completely ordered, almost ordered. That's the best algorithm here in insertion sort. Almost sorted. The fastest one is the inversion sort. All right, just recall this problem. Okay, all right. Now, how to merge two sorted array. Take a different view on insertion step. Now, we want to look at the insertion step again, but this time we try to generalize our view and try to connect it to the merge step. All right. Why take a different view? Because we want to get inspiration for a new idea. Inspiration. All right, so look at this as a typical insertion step. We need to insert that V in an already ordered array. That's our typical insertion step. We know how to do it, right? You're familiar with the standard insertion step. So here, how do we connect to the merge step? You know the merge step. We just describe it. Yeah, all right. It looks like not the same, quite different. These two steps quite different. But if you look at a similarity, part of it the same. Can we imagine that single key element, can we treat it as a one element array, also ordered? Because one element array is ordered. But this time you have two subarrays, okay? Both ordered. Although that one element is very special, but it's a special case of an ordered array. So this time we merge two ordered arrays. What? It's a special case of ordered array. And in this part C, we need to merge two general ordered arrays. That's the main difference. Yeah, but with experience in the insertion step, now we need to extend it to the new merge step. That's what we need to do. So our new interpretation, two sorted arrays are combined to get a new sorted array. The merge step, very similar to the insertion step, but we need to modify a little bit to cover the more general case. All right. So the new view, we merge two sorted arrays for a new sorted array. Okay? Yeah. All right. Yeah. So here you can see we convert insertion type manipulation to merge type manipulation. That's the key change. That's the most important change. Apply new merge view here. For the insertion step, our data size, first one k element, second one element. So you can see, the size difference is very big. Right? So we call it not balanced. It's not a balanced data split, right? Yeah. If you have freedom to choose, you don't want to make this kind of split. Okay? When you have freedom to choose, if you do not have the freedom, then you can only take it. But if you have some freedom to choose how to split your data, you won't make the split. Because if the data distribution is too unbalanced, then it will respond to worst case. Worst case. We want to get fastest worst case. The efficiency won't be good. We want to do better. So we want to make a balanced split. Poor worst case. The consequence for the data split like this. Poor worst case. Even if we always work on the worst case. But sometimes the worst case is very bad. So we want to make our worst case the best we can. We want to get the best worst case numbers to improve performance for the worst case. We want to apply the balancing principle. Balance. When you have freedom to choose, you want to choose the most balanced way to split your data. That's the balancing principle. Okay? Try to make two subarrays of equal size. If we can choose how to split the data, that's the best way to split our given array. Okay? Equal size. All right. Sequence 2, merge operation. Now let's look at the details of the merge operation. How to achieve balanced subarrays. Here, let me describe the split idea. Very simple, straightforward, just by our intuition, we can do it from beginning to end. Here I use some diagram to describe this idea. Whenever we merge two subarrays, we make them of equal size. First, we do split. Divide and conquer. Yeah. Split, that's the divide step, right? Yeah. Divide step. Even split. Then we conquer. Conquer each subproblem. After we conquer it, then we need to combine the two subproblems to get back to the original problem. Combine. Combine, that's the merge step. Here, let me use a diagram. Okay? When we start, we have the whole unordered array. Divide and conquer. Let's do divide and conquer. The first split, divide, make the split as even as possible. Yeah. Yeah. You know how to do it, right? As even as possible. It depends on you have even number of elements or odd number of elements. Even two subarrays have the same size, or one is one more than the other. That's the most evenly split, as even as possible. All right. The first split, right in the middle, two subarrays. Divide, that's the divide step. Then conquer. Then conquer. Conquer, we just assume we apply recursion to do the conquer. Recursion. How to do the conquer? We call the function recursive. Okay? So we don't worry about the conquer step because we can call this function recursive. Okay? By recursion, we conquer it. Okay? We conquer it. Then, because when you conquer, you need to split another time, right? Yep. Recursion. That's recursion. You need to split another time. The second round also evenly split. Second round. And so on. Keep splitting, even splitting in this way, all the way to the last level, bottom level. What's the bottom level? When the current subarray size becomes only one element. You cannot split anymore, right? One element. How can you split anymore? You have to stop when you reach the one element subarray. You have to stop, okay? Yeah. Then you can start merging. Because you reach the very bottom, you can start merging. Okay? Yeah. All right. Merge, every time merge two adjacent subarrays. Two adjacent subarrays to get an ordered, larger subarray. The first round. Okay? Going back, first round. After that, second round, merging two adjacent ordered subarrays, and so on. Next round, merging. Okay? Yep. Ordered, larger subarrays. Keep going like this. Merging every time two adjacent subarrays. Yeah. Larger and larger. The last merge, because you only have two ordered subarrays before you get your final destination. The last merge, you get a whole array order. How about the sign here? This is merge sort, right? Divide and conquer. Merge sort. Basic merge. When you merge two adjacent subarrays, we apply our basic merge step. If you have the solution of the basic merge step, then using this divide and conquer approach here, you can complete the whole merge sort. That's the main idea of the merge sort. Okay. So now, the only missing piece, basic merge step, right? That's the only missing piece. After we finish that, key piece, we complete the whole merge step. All right? Yeah. Hope it can avoid poor worst case. Here, what is this comment? What's the meaning of this comment? Let me explain a sentence. Why I say, when we do this, because people may ask you, why we do it this way? We have so many different ways to do the sorting. Why you take it this special way? There must be some reason to do it this special way, right? Yeah. If you want to answer that question, here, the answer is right here. We hope by taking this special way, we can avoid poor worst case. Why we can have this kind of hope? Because think about it, evenly split. Every time we do our data split in this even fashion, we know even fashion, that's based on the balancing principle, and the balancing principle has the biggest property. It can help us avoid poor worst case, like balancing principle. So that's the reason we have this form. All right? And you will see, we will get it. You will see later when we do the analysis of efficiency. We will get it. Okay? No, we will get it. This problem, a nice problem, we will get it. next, we need to work on the merge step. So here, I want to use this diagram to show you the basic idea of the merge step, the standard merge step. Let's merge these two ordered subarrays, both ordered. Then, the first comparison, here, when we do our first comparison, you can see we pick two smallest elements in these two subarrays. A0, that is the smallest element in the first subarray. B0, the smallest element in the second subarray. Let's compare these two elements first. Which one is smaller? Which one is larger? The smaller one, here we call it as min 0. Min 0, the smaller one. The larger one, we call the max 0. Okay? Now, after the first comparison, the min 0, that element, we know it must be the smallest element of all, right? That is the smallest element of all the given data. That means we can put it in place. It's smallest. We know its place, right? In our destination array, we know its place. So we can put it right in place. After first comparison, we put the min 0 in place. Okay? Now, let's keep going in this way. Because the survival at max 0, remaining one, max 0 still, we don't know its place, right? Max 0, we don't know its place. So for max 0, we use it to compare with A1. Okay? The next one in the array. After we remove M0, because we put it in place, we can eliminate in the original data. So the next one in the pipeline, A1, we compare it with max 0. So we should have a smaller one, min 1, right? The smaller one we call the min 1. Okay? Then we put a min 1 in place after the second comparison. Min 1 and the max 1 should be left, right? The max 1. Max 1, so we can consider with the next one, but we can keep going. Every comparison, we can put at least one element in place, right? The minimum we can do, put one element in place. Why I say the minimum? Because we have chance to do better than that. After one comparison, we have a chance to do better than just put one element in place. What's that case? Why I say after one comparison, we can do something better. Think about, suppose there is a BI in the middle somewhere. This BI, if we do comparison with the last one, because this BI beats all the 8 elements, okay? After this last comparison, BI beats AK minus 1, then all the elements after BI can be put in place, right? Without any comparison. If BI beats all elements in A subarray, then the elements after BI, we don't need to do any more comparisons, right? So we can just copy them into our destination array directly without any comparison. That means each comparison we can put at least one element in place. We can do better than that. The worst we can do one element in place. All right. So now you can see we can finish the merge step like this. merge step. Yeah. Until we put all elements in place. Yeah. The last one we do not need to do comparison, right? Yeah. In one. The last one we can put it right into place. Okay? All right. Now we need to consider the best case and the worst case. First, the worst case. What is the worst case? How many comparisons do we need for the worst case? We need to do, for the worst case, we need to do comparisons all the way,
2k minus 1.
right, not the last one, right before the last one.
But it's minimum 0, so then that adds 1. It's a 2k minus 2. So that's 2k minus 1.
Yes. Good. Very good. Yes. Yeah. Perfect. Perfect. You give me the perfect answer. 2k minus 1. Or you can view in this way. What's the number of the total number of elements? What's that number? A subarray we have k elements, right? A subarray we have k elements. B subarray we also have k elements. K plus k, 2k. Total number of elements we have 2k elements. So the number of comparison, just the total number of elements minus 1. Because the last one we do not need to do comparison. The last one, no comparison for the last element. So that is 2k plus 1. In that case. Worst case, here we can get this summary. When we merge two subarrays, the worst case number of comparisons, total number of elements minus 1. That's the summary. Worst case. Now the best case, let's work on the best case in the next slide. Best case. Yeah, but here, before the best case, let's do the general merge step. General merge step, that means the number of elements in A subarray and the number of elements in B subarray and N and N could be different. That's the general merge step. Not necessarily the same.
What was the other case called? So this is called general merge step. What was the other one called?
Yes. Yeah, general merge step. Worst case. Yeah. Because although we like to even split, but in the real world applications, we may need to solve the problem using the general merge step, right? So we want to consider the general merge step. Then the worst case, based on the summary from the previous slide discussion, the total number of elements minus 1, right? Total number of elements m plus n minus 1. The answer, m plus n minus 1. That's the one. Yeah. First case. Next, the best case. The best case. Yeah. Won't be much harder. Yeah. So the idea also pretty simple. All right, look at this slide. The best case for the general merge step. Okay, now, this time, let's go the extremo case, the other direction. The best case. First, let's try to see which situation corresponds to the best case. Best case. The strategy. How to see the best case, the strategy. try to exhaust one of the two arrays as early as possible. Exhaust. You complete process. Exhaust, right? You put them in place. Then, one of the subarrays, we run out of elements for one of the subarrays as early as possible. We want the fastest way to put all the elements in one of the subarrays in place as early as possible. That is, think about it. One possibility, B0 beats all the elements in A subarray. How about that? B0 is greater than all elements in subarray. When you do comparison, B0 always the winner. Okay? Yeah. So all the elements in subarray are placed in its right place immediately. Yeah. Alright? So the B0 is still there until we put all elements in A subarray in place. After that, we don't need to do more comparisons, right? After that, we just put all elements in B subarray in place. That's the first possibility. How about the second possibility? A0 beats all elements in B subarray. It's also possible, right? The other way around. This time, A0 is greater than all elements in B subarray. So then we should put all elements in B subarray in place first. Then A elements in A subarray after position of elements of B subarray. That's another possibility. These two extreme possibilities. Then, what is the best case number? Based on this observation, what is the best case number?
The minimum of the value of m or n.
Correct. Minimum of n and n. Because n and n may have different values. We want to take the smaller of the two numbers, not the larger one. Okay? We don't want to take the larger one. We want to take the smaller one. So the best case, so we exhaust the shorter. Then we can do fewer comparisons. Shorter, the smaller number of n and n. Okay? So the best case efficiency, the answer, minimum of n. That's our standard merge step. Now we understand the standard merge step completely. Okay? After you understand this, I hope you completely understand this basic merge step. Because later we will have many questions based on these two formulas. The best case formula, this one, and the worst case formula from the previous one. We have many questions. Okay? Now, get ready for that. So that's after midterm. After. All right. Still, we haven't finished the merge sort. We have last step of merge sort. Efficiency analysis. How do you know we can get very good worst case efficiency? That's the last thing, last question we want to answer. Worst case efficiency. All right. C13. Efficiency analysis for merge. This time, we need to derive recurrence relation first. Recurrence relation. Yeah. Okay. based on the divide and conquer, we want to write the recurrence relation explicitly. Based on the worst case efficiency. Worst case efficiency. All right. We start with this array, general array. Let's assume the total number of comparisons to solve this whole array. Capital T function, T of n. That divide and conquer split right in the middle. Number of comparisons. Make even split. All right. Two subarrays. The size, let's assume the same. Okay. Although there is some small difference we need to consider, but we can use approximation, right? We can estimate. Good approximation. All right, so let's assume to conquer each subarray, we need this T of n over 2. The problem size n over 2, and still the same T function gives us the number of comparisons for one of the subproblems. The second one also T of n over 2. So we need to add these two numbers because we need to conquer each subproblem. So we need to pay the cost covering both subproblems. And more than that, right? After we conquer individual subproblems, we need to combine, we need to merge. There is merge cost, right? There is merge cost. Total number of elements minus 1 for the worst case. That's the merge cost. Let's use approximate number n. That minus 1, we use good approximation n. Small difference. We want our equation as simple as possible. So we drop that minus 1. Okay? We draw. There is minus 1 there. We drop it. Okay? Not big deal. All right. Now, this is the recurrence. T of 1 element, no comparison, right? So T of 1 equals 0. T of 2 elements, 1 comparison. Get it sorted, right? So T of 2 equals 1. Other than that, T of n equals 2 times T of n over 2 plus the merge cost n. That's our recurrence relation. Now we need to solve this recurrence relation. It may not be very easy. It may not be very easy, right? Yeah. Okay? It may not be very easy. Yeah. But here, let me use some simple way to estimate it first. Let me show you a simple way to estimate this T function. Estimate. So that's different from guess. So when you do guess, sometimes you need to do some imagination to make a guess, right? And here, actually, we want to get some critical information to estimate this T function. All right, so let me show you how to do it. Estimation. Consider a simpler case first. because here this n over 2 pretty complicated. Now, n over 2, when n is an integer, n over 2, sometimes it's an integer, sometimes not an integer, right? Although we can apply floor function, ceiling function, but still too complicated, right? Even floor function or ceiling function. All right. So remember, there is, for this basic strategy we used many times, when we start, we want to consider some special, so simpler cases first, not the general case. To get easy start, we want to consider special, easy cases. Here, can you imagine certain special case can make our equation easier? Certain equation can make our equation easier. First, can we assume n is an even number? We have two options, n even number and an odd number. Which one is easier for us? Even number, right? Odd number, harder for us, right? Yeah. So when there are two options, we pick the easier one first. The first time, we always pick easier. First time, we don't pick harder one, okay? Harder option. First time, easier option first. So the easier option, n is an even number. But because we need to do recursion again and again, every time we want that n even. How can that happen? If we make this assumption, n is power of 2, then every time when we do n over 2, we get integer, right? So this n, this type of n, power of 2, is the best we can imagine. Because after we make this assumption, n equals 2 to the k power, then all the division by 2 becomes integer. How nice it is. Division by 2, all integers. Yeah, we don't worry about fraction case. Yeah. All right. So then we rewrite our recurrence relation in this way. You won't see any denominator, right? After this transformation, you won't see any denominator.
Recursion.
Yeah. So t of 2 to the k equals 2 times t of 2 to the k minus 1 plus 2 to the k. All right. So that's the first round transformation. Make our equation easy. But still not good enough, right? Still not, we cannot see the answer from this equation. We need to do another round transformation. Anyone has any idea to do some special transformation? Special transformation based on the structure you view here in this equation. The structure. Lot of power of 2. Look at that structure. Lot of power of 2. Nice structure. We can make use of power of 2 structure. How to take advantage of power of 2 structure. Right? So that's one useful piece of information. Another useful piece of information. Then we give a sign. 8. I remember we did similar things before. Here, let me remind you a little bit. Something we did before, similar. Okay? Let me recall our whole experience a little bit. When we solved the recurrence relation for the Tower of Hanoi problem, remember that? The Tower of Hanoi problem, what's that? Cn equals 2 times C sub n minus 1 plus 1. That's the Tower of Hanoi problem, right? When we do that, what special transformation did we do at that time? Special transformation. Anybody?
We let 2 with Cn minus 1 plus 1 equals like 2HMN or something? Forgot.
Not quite there. Yeah, let me just remind you a little bit. All right. Yeah. Left-hand side structure, right-hand side structure, not quite the same. Because at right-hand side you have plus 1. Left-hand side you don't have plus 1. So the structure-wise, quite different. Our idea, we want to make left-hand side, right, they have the similar structure. The question, how to make the left-hand side, right-hand side, the similar structure? There is a special operation we can make the two sides with similar structure so we can we have a better way to do it. The y method plus 1 both sides. How about that? Plus 1 both sides. Plus 1, then after that, Cn plus 1 equals 2 times Cn minus 1 plus 1. Can you see the similar structure? Both sides. Similar structures, both sides. Can you see that? That's what we did in our old recurrence relation solution. Can we do similar thing? We do one special operation right here to get both sides similar structure. The structure is quite different. Yeah. But after one special operation, power of 2 related to power of 2, we can make both sides with similar structure. Anything like that we can do here? Anything we can do special here? Division method. Division. Division by power of 2. 2 to the kth power. This transformation. Division. After this, after cancellation, can you see similar structure both sides? Are they look the same? Similar structure? Can we treat them same structure? That's a nice thing. We want to reveal, right? Before you do this transformation, you cannot see the similarity, structure similarity, right? But after this special transformation, we reveal this special structure similarity. Okay, all right. Then, the next step, how do we continue? We take advantage of this structure property, and then we go to the next step to find a solution. Define a new function. To get a better view, because we want to see things clearly, to get a better view, we want to introduce a new function g of k that equals this fractional expression. T of 2 to the k over 2 to the k. A new function that can simplify our old expression. After this g function definition, we have here next step, substitution. Let's do substitution. All right. Our new
Can you go back a little bit?
okay. Oh yeah, no problem. That's too fast because it's near the end of class, so I can move a little faster. But we're fine. We will finish it quickly. We still have a video. We still have a video. Video study. All right. We've done. Next slide. We have last 5 minutes. Good. Last 5 minutes. All right. Substitution method. Now, update our recurrence relation. Replace that fractional expression t fraction by this new function g of k equals g of k minus 1 plus 1. Is this new recurrence relation much simpler? Right? Much simpler. Right? Yeah. So simple. Can you solve it quickly? Right? Yeah. We know, because we need to know the initial value of g. When you plug in k equals 1, we get a g of 1 equals 1/2. Initial g function value. Do one iteration, g of k minus 2 plus 2. Yeah, because we replace g of k minus 1 by g of k minus 2 plus 1. 1 plus 1, 2. Okay? Can you find some rule when we do this iteration again and again? Can you see some special rule so we can keep track of all our equations? Otherwise, we cannot keep track of our equations. We get lost. We want to keep track of all our equations. How do you keep track of our equations? Invariant method. Do you still remember some invariant method we learned before? Invariant. We need to discover some special invariant. Add k minus 1 with 1. What's that number? K minus 1 and 1. Okay, what's that number? That's k, right? Look at that. This k will be our invariant. Add k minus 2 and 2. What's that number? The sum of these two numbers. Also k, right? Yeah. We keep going and we always get this. Here we add in the two numbers here. We always get k. We always get k. Right? So we keep track of all the equations with this invariant number. Okay? Yeah. When we reach the bottom, what is the bottom equation? The bottom equation, g of 1 plus k minus 1. The bottom equation, right? G of 1, we know that's 1/2. Okay? 1/2. So that gives us the answer. G function equals k minus 1/2. But that's G function. We need to go back to the T function. Yeah. So we need to do another step for the T function. T of 2 to the k equals big parentheses k minus 1/2 times 2 to the k. But we need to go back to our n number. N number. N equals 2 to the k. Okay? So we need to use the n as our variable. So t of n, k becomes log n, log base 2. Okay, log base 2. So t function becomes t of n approximately equal, because this 1/2 we can drop it. Too small, we can drop it. Okay? Yeah. K, we replace K by log n. Okay? 2 to the K n. So T of n approximately equal to n times log n. Log is 2. That's the good approximation, right? That's better than guess, right? Although n, we work n as power of 2, can we reasonably assume when n equals the general number, we also have this approximation? Reasonably, right? At least we can guess like this, right? Yeah. Actually, it's also correct. For the general n, we also have this approximation. Okay? Yeah. That's the end of merge. So we